Hi everyone. So today's lesson, and really today's lesson and tomorrow's lesson, are going to focus on the graphs of variation functions. So the different types of variation we've talked about, each one creates a different type of function and a different type of graph. And so our job right now is to learn what those shapes of the graphs look like and their various properties. So we're going to start out with just real basic direct variation here. And when I say direct variation, what I'm talking about is just y equals k times x. No exponents or anything, just y equals k times x. So in order for us to do this, I'm going to make up one of these functions, which basically means I'm going to pick a k value. And we're just going to create a function and create a table that goes along with it. So I'm going to say, let's work with y equals 3x. Okay, that is a direct variation function. By the way, I should mention, I'm going to be talking through basically everything you need to know about this type of function. In your notes, you have a table where you're filling in all of this information. So you can fill that out as we talk through it if you'd like, or what I would actually recommend is watch maybe the first part of the video for all of the direct variation information, pause it, and then fill in your table with everything that you've seen. Okay, so that way you're not kind of splitting your focus. So let's just make a quick table of what y equals 3x would look like. And because I'm trying to graph here, I'm just picking some negative x values and some positive y values, or x values, sorry. And if I plug those in for x here, 3 times negative 2 would give me a y value of negative 6. 3 times negative 1 gives me negative 3. 3 times 0 is 0. 3 times 1 is 3. 3 times 2 is 6. And then if I go to try to graph this thing, let's see, did I leave enough lines here? There we go. 3, 4, 5. May have to go up one more there. And then 1, 2, 3, 4, 5, 6. Okay, so if I'm plotting these points here, negative 2, negative 6 would be way down here. Negative 1, negative 3 would be here. 0, 0 right in the center. Oh, I can already tell that my this is not the most perfectly drawn graph ever. Here's 1, 3, and then 2, 6. So what you should see is a perfectly straight line. We'll pretend here that my graph is drawn better. But the point is, any one of these functions, any one of these direct variation functions is going to give us a line, a straight line as a graph, okay? These are linear functions, and you actually worked with these back in 8th grade. You've talked about these before. So a couple of things that we need to notice about this linear function. First of all, the name of this thing, we would just call this a line. I'm only saying that because I think there's a spot in your table where you have to say what the name of the graph is. Let's talk about domain and range, which are our favorite things to ask you about functions. So domain is asking, what is x allowed to be? What does my graph cover going left to right? And because this graph would go on and on forever, it's eventually going to stretch out to the right forever and to the left forever. Also, if you think about the equation, there's really no restriction on what I can put in for x here. I can multiply anything by 3. So my domain is all real numbers. Now the range I always find to be harder thinking about from the equations perspective, but on the graph we can see that this graph goes up forever and it goes down forever. So any y value along here that I choose, I should be able to find a corresponding point on the graph for. And that means that my range would also be all real numbers. So I could get any number I want to come out here in the y column by choosing the correct x value to go with it. So there's domain and range. And then the other thing that we need to make sure we are aware of is this graph is always going to go through that center point 0, 0. So the intercept that we want to be aware of is 0, 0. Let's think about that mathematically for a second. Anytime x is 0, y is also going to be 0. It doesn't matter what my k value is. So these numbers here would have changed if I had chosen a different k value, but this 0, 0 is always going to stay the same. So it's important to know that when you're working with linear functions, at least direct variation linear functions, because we are going to talk about other types later on, but anytime you're working with direct variation, that point 0, 0 is going to show up there, okay? Now, there's another thing that you learned when you first learned about how to work with linear functions back in 8th grade, and that is that linear functions have something called a slope. The slope is the measure of vertical distance compared to the measure of horizontal distance. So for example, to go from this point to this point, I go up 3 and over 1, okay? And then to get from this point to this point, I also go up 3 and over 1. That value is always going to stay constant in a linear function. So the slope is a comparison of vertical change to horizontal change. And I do believe there's a place in your notes to mark this down. But the important thing to know about this, the reason that slope is important specifically for linear functions, is that when we're talking about something linear, that rate of change is constant. I suddenly forgot how to spell constant. Okay? So rate of change in a linear function is constant, which means if I want to go from this point to this point, I'm going up 3 and over 1. If I want to go from this point to this point, it's up 3 over 1. That value is going to stay the same over time. And then I also want you to notice that the fact that I'm going up 3 and over 1 has to do with this equation, right? I chose a k value of 3. So in a linear function, the k value gives you your slope. Oh, you can't see what I'm writing, sorry. So the k value gives you your slope when we're talking about linear functions. Now, when we talk about other types of variation functions, they don't have a slope, and so the k value does not really have a significance there. But when we're talking about this type of function, the k value is the slope. So that's all the information you need for the first row of your table. I do want to take a second and talk about what happens if we put a negative k value in here. But if you want to pause right now and fill in the first row of your table, this would be a good time to do it. So now let's say that I was going to work with y equals negative 3x. I want you to think about what that would do here in my table. So y equals negative 3x. If I multiplied, and actually maybe I'll just make a new table. Not like that's too hard. So now when I go negative 3 times negative 2, I'm going to get positive 6. Negative 3 times negative 1 gives me positive 3. My 0, 0 is still there. Negative 3 times 1 gives me negative 3, and then negative 3 times 2 gives me negative 6. So look at these y values compared to these y values. Basically everything's switched, right? This is changing all my y values from positive to negative or negative to positive. So when I go to graph that thing, negative 2 is now going to go to positive 6 up here. Negative 1 is going to go to positive 3. My 0, 0 stays the same. 1 now goes with negative 3, and 2 now goes with negative 6. And so now I still have a linear function, but notice that it points the opposite direction. So a negative k value is going to lead to a negative slope. Negative slope just means it's pointing downward. Okay? So I'm going to just make a note of that down here, that when k is positive, my graph is always going to look like this. Whoops, and it should go right through 0, 0. Make a big origin there. When my k value is negative, it's important to know that my graph will always point this way. Okay? So positive slope versus negative slope. Difference between the two. Now, as far as those properties go that we talked about back here, those are all still going to be the same, because even on this function, my domain, it's still going to go forever left to right. My range is still going forever up and down. It's just pointing the other way, and it still goes through 0, 0. Okay? Okay, so we're going to move on now to direct square variation. Again, if you needed to pause to get your table filled in, you certainly may. And I believe I posted this with the announcement, but you do not have to worry about that last column where it says limits. The very last column on your table you do not have to fill in, but you should be filling in the name of the graph. You should be sketching a picture of the graph, which is here. You should be giving domain, range, and then the intercepts. Okay, those are the things that your table is asking you for. One more thing to throw in on slope here quickly before we move on to the other type of graph is you've probably learned the equation for slope before. The equation for slope looks like this, y2 minus y1. I guess I should say the formula for slope, not the equation, but x2 minus x1. What this is really doing, that y2 minus y1, that is your vertical change, right? And then x2 minus x1, that's your horizontal change. So if I wanted to find the slope using these values back here, I could pick two of these coordinates, let's say -1, 3, and 2, 6. So I could go y2, which is 6, minus y1, which is -3, over 2 minus -1. Now, anytime I'm doing minus and negative, that's really going to become a plus, right? So this would become 6 plus 3, which is 9, and 2 plus 1, which is 3. And then take a look there that 9 over 3 is really just equal to 3, which we said was our slope back here. Okay? So I just wanted you to see the connection between this calculation of slope and the value that you're going to find there in your k value. Okay, let's move on to some inverse square graphs. All right, so now we're going to talk about a different type of function. We're going to talk about the direct square variation, which is still direct variation, so it's still k times x, but now we're going to throw a square in there. So we're going to say kx squared. And so that's the equation that we're working with. Just like before, I'm going to make one of these up. I'm going to use the equation, I don't know, let's say 2x squared. Okay, so we'll make our xy table. All right, and then I'm going to run through these calculations by hand because I want you to see what I'm doing. And I'm going to start with the 0 here. So first I'm doing 2 times 0 squared. Well, keep in mind that order of operations says I have to square the 0 first. So this would really just become 2 times 0, which is 0. And once again, just like the graphs that we worked with before, this 0, 0 is always going to show up on one of these graphs, as long as we're talking variation here. Because anytime I plug 0 in here, the answer is going to come out to be 0. So when I go to do 1, that's 2 times 1 squared. Remember, I square the 1 first. 1 squared is 1, so 2 times 1 is 2. Plug in the 2, 2 times 2 squared. Well, this 2 squared would be a 4, so this is really 2 times 4, which is 8. Back here, 2 times -1 squared. And notice I put it in parentheses because if you're putting it in a calculator, it has to be in parentheses. -1 squared is really just 1, so this becomes out 2 times 1. Notice that's exactly what you have down here, because when I square those negatives, they're all going to turn into positives. So we should actually find that the bottom half of our table matches the top half exactly. And then 2 times -2 squared. Well, -2 squared is 4. So just like before, I have 2 times 4, which is 8. Okay, so this graph is going to look a little different, and I'm going to sketch one here quickly. Doesn't have to be anything fancy. Oh, didn't go down quite low enough. We need to go to 8 here. 3, 4, 5, 6. Okay, tried to space things out appropriately there, but. All right, so let me plot these. So -2, 8 would be here. -1, 2 would be here. 0, 0 is here. 1, 2 would be here, and then 2, 8 would be up here. And notice that kind of symmetry there, right? That these points all match. That's because of that squaring thing that we talked about. Now, I know it's tempting to just draw this like a V. It's not quite a V. If we had more coordinates on here and if my graph was drawn better, you'd be able to see that there actually should be a little bit of a curve to this. It should look more like a U. Okay, that's what this graph is always going to look like. And this is called a parabola. Not parabola, parabola. All right, so let's talk about our properties here. Domain, if I go left to right on this graph is eventually going to spread out and cover everything. So my domain is all real numbers. And also, if I look at the equation, there's no restrictions on what I can put in for x. My range, though, is going to be a little bit different. Notice that I never get any negative y values. It's impossible to get a negative y value over here because everything that gets squared gets turned positive. So for my range, I'm going to say all real numbers greater than or equal to 0. And I included the or equal because it does actually touch 0 there. Okay? And then this graph also will always contain the point 0, 0. Okay, so there are those properties that we're worried about. Okay, now let's think about what happens if I make my k value negative. And I think I can sketch this really quickly here for you. If I made my k value negative, down here in the table, all of these 2's would become negative, right, when I multiply. And so what that's going to do is make all of my answers come out negative. Now, negative 0 doesn't really make sense, but just a second ago, we said that we were getting all positive numbers here for y. But when I switch my k value to be negative, suddenly I get all negative numbers. So think about what that's going to do to you picture-wise. At negative 2, we used to be up at positive 8. Now we're going to be down at negative 8. Okay? And I guess I'll go ahead and sketch that. At negative 1, we were up at 2. Now we're going to be down at negative 2. 0, 0 is still going to stay the same. And then here's where those other 2 points would lie. So now we're going to be looking at an upside-down parabola. So this graph represents when k is positive. This graph represents when k is negative. Okay? So these properties that we listed here a second ago, this was all for when k was going to be positive. When k is negative, one of those properties is going to change. Not my domain, because this graph still covers everything left to right. It still spreads out forever to the left and forever to the right. So my domain is still all real numbers. My intercept is still at 0, 0. What will change here is my range, because just like I said a second ago, before we were getting all positive numbers, all numbers above 0. Now when I make my k value negative, I'm going to get all numbers less than or equal to 0. Okay, so that's really just a matter of knowing which way your parabola points. So takeaways here. I want you, when you see this type of equation, to immediately associate it with a parabola, to know that it's going to make this U-shaped type graph, and that k value, being positive or negative, is going to affect which way my parabola points. Does it point upward or does it point downward? That will affect the range. It should not affect either of the other 2 properties that we're concerned about. But the range is what you want to pay attention to in terms of your k value. Okay. That was really it on that. So that should be enough for you to fill in the top half of your table. That's what today's lesson is covering. And then there should be a separate video talking about the rate of change problems that was covered in the rest of this lesson. Okay? All right. Thanks a lot. Have a great day.